Determine all points where the curves, so we got two parametric curves here, one where the x-coordinate's given by 3t and the y-coordinate given by t minus 3, and the next one, t squared minus 1t for the x and y. Determine all the points where they intersect. Okay, when doing intersection between two curves, you cannot have the same t value. It's forbidden, because these two curves, while they might be tracing out and intersecting the same points, use red for the other one, they might not do it at the same rate. And so the red curve might have t equals 2 for this point, and the black curve might have t equals 1/3 for this point, right? So you cannot be sure. So the first thing you should always do, I see the same parameter here. I don't want to goof, because if you forget to change them, you'll be saying, oh, okay, the x coordinates have to be equal. Well, that's a quadratic. That's not a problem. But then the y-coordinates have to be equal, and then, oh, you cancel out the 2's, minus 3 equals 0. No points of intersection. No, these two curves do have some points of intersection. Okay? But if you forget to change the variables, that's exactly what's going to happen. So you pick one curve, whichever curve you like, whichever curve you dislike, whatever, it doesn't matter, but you give it a new parameter. I see t's, so I'm going to stick with s's for my second parameter. And so the one curve we will keep as 3t, t minus 3. But the other curve, we will make it s squared minus 1, s. I'm just going to go back and double check, make sure I copy both of these correct, because nothing worse than finding the points of intersection between the wrong curves. But everything looks good there. And so as I was showing, what do? We set the x-coordinates equal. Now it doesn't look so simple. I mean, yeah, it's technically a quadratic, but it's a multivariable polynomial, multivariable quadratic, so, and then what have we got here? T minus 3 equals s. And what we want to do is just solve for s and t pairs that make left-hand side equal right-hand side for both. Okay. It's really just a game of algebra now, no sort of fancy tricks. I do notice this last equation here, we already have s in terms of t, so what I'm going to do, I'm going to take that, I'm going to put it into the first equation. So 3t here is t minus 3 squared minus 1. And then I can expand this out. This isn't the only way to do this, by the way. You could do something else like rearrange the first equation to get t is s squared minus 1 all over 3. But I think this is probably the easiest setup here. So t squared minus 6t plus 9 minus 1. And we can bring the 3t over to the other side here. Can we factor this? Absolutely we can. I get t minus 8 and t minus 1. So this gives us my t values. T is going to be 8, or t is going to be 1. And each of those we should be able to solve for an s value. You should always solve for your t's and your s's, especially if it's a way more complicated parametric, just to make sure you're not missing something. Because sometimes, and it's not a very common thing, but it does happen, sometimes you're so focused on getting a single equation with t, and you solve it, and you don't realize that maybe some of these t values don't make sense for s. I'll give you sort of a short example of what I'm talking about, then we'll get back to the question. But let's say the equations were just ever so slightly different. This is not going to be like a real-world working example. But if the equation had been something like log base 2 of t equals s, and you plug this s in here, and you rearrange, and you solve, and you say, oh, t is 8, or t is minus 1, because you're solving just an equation in terms of t. Okay? You might not realize, wait a minute, 8 you can plug in, and the second equation you'll have left-hand side equal right-hand side, but if you plug in t equals minus 1, log base 2 of minus 1 doesn't make any sense. And so even though you've solved some fantastic polynomial that you've set up in t, it doesn't mean that there is a corresponding s and that there is a point on the other curve that really does work. Okay? So, obviously this is a broken example, because if you take this expression for s and plug it in here, you don't get this quadratic. But the idea is always solve for your s's just in case something has sort of broken, because this happens a fair bit, not too much, but it does happen a fair bit when solving with lots and lots of variables. Well, here we've got 2 variables. And typically a strategy is isolate one variable and then get an equation or equations just in the other. But sometimes this equation makes sense and can be solved, but the original equations that you combined maybe can't. Maybe there's some little defect that got canceled out. that you won't notice. So always, always, always solve for your s's as well. In this case, no such issue. S here is t minus 3, so if t is 8, you'll get s is 5, and if t is 1, you'll get s equals minus 2. And then plug them in and get the point of intersection, and I recommend you plug in both. You should, for each of these pairs of t and s, get the same point. So plugging t equals 8 here should give me the same thing as plugging in s equals 5 here. And same thing with t equals 1 and s equals minus 2. We should get the same ones, but let's verify that. All right, it never hurts to take a little bit of extra time. So 3 times t, and then t minus 3. And you'll get 24, 5, so that's the 1 point. But it never hurts to verify this, and sometimes it can catch big mistakes. Okay. So 25 minus 1, 24. Oops, 24, 5. Yep, this is a point that is on both curves. Okay. And the other one, t equals 1, s equals minus 2. So you'll get 3 times t, and then t minus 3. So you'll get 3, negative 2. And then negative 2 squared minus 1 and negative 2. You can get 4 minus 1, which is 3, negative 2. There we go. So 24, 5, and 3, negative 2. These are the only points of intersection. There they are. These are our points of intersection between these two parametric curves.